right, everybody. Let's see. Okay, what's going on? We got the audio going on, and I do think we should have the length here. So let's double check. 261. Did I put that there? I believe I did. Okay, I think we're okay. So I'm going back over here. We do have the link now. Let me go here to you guys. Remember, there's a couple of things that we want to talk about. If you guys remember yesterday, what did we work with? Do you guys remember what we did? We approximated what? Area based on these what? These different formulas. You guys remember that? Right endpoint, left endpoint. So let me go back to this portion right here maybe, okay? So in my notes, let's go back here. We're going to erase all of these things here for you guys. Let me see if you guys can see this. Okay, let's erase all of this. Because today is a glorious day. And let's go through the assumptions here again. This is everything we did yesterday. We approximated area under a curve. And this is all based on, if you guys recall, using rectangles. Okay, this is delta x. Now remember what we did. We partitioned the interval AB, okay, into what? N subintervals of equal length, delta x, and that's what we did. And we had various formulas. Yes, delta x is b minus a over n, okay? And so to generally write what we did here, you say, what do we generally do? Well, we took the sum of f of, I'm going to put this f of xi asterisk delta x, okay? Because what I just did was give you like a general, you know, let's go back to the color blue, I guess. Where this xi asterisk, okay, is in your interval that we have in this picture. And this is a very special point in the interval, so you guys know. And that point can either be a left endpoint, it could be a right endpoint, it could be a midpoint value. We really say it's just an arbitrary value in that interval, okay? And so you see this sum that you guys have here, where I goes from, it starts from 1 to n, all in theory, okay? And so there's this finite sum of rectangles that approximate your area, okay? Now, this is called, by the way, a Riemann sum. But let me actually give you guys some more information. The question is now going to be this. Okay? Yes, your area is approximately this, right? This is an approximation. We've seen that yesterday. But what happens now is we're going to let n go to what? Infinity. And you guys say, what are you talking about? N is going to go to infinity. Well, the number of partitions is not going to be like 5 partitions, 10 partitions. It's not even going to be 100. It's going to be what? Arbitrarily what? Large. Number of partitions. N is going to what? Infinity. And you go, oh my God, that's going to blow your mind. So you're going to get more and more of these approximating rectangles. In fact, there's uncountably approximating rectangles. Notice when n goes to infinity over here, by the way. What are you really saying? If n goes to infinity, that delta x goes to what? 0. Is that right? So that small increment goes away. There's no longer a delta x. That's going to 0. Now, when you do this, that's a very special thing. What that now means is you're taking the limit now as n goes to infinity of the sum I goes from 1 to n f of x asterisk delta x. Where the area now is no longer what? Approximate. This is now what? What does that symbol mean here? You have an exact area. All right, you guys with me on this? Now, it gets better here. Okay? Let me move this up. All of this is a definition of what we call a definite what? Integral. And that's in your book. Yes, it assumes again f is what? Continuous over that interval AB. That's an important thing. Okay, f needs to be continuous over the interval AB. But they now introduce this notation for you guys here, okay? This is your definite integral what? Notation. And it's defined to be the limit n goes to infinity sum I equals 1 to n f of xi asterisk delta x. So I'm going to give you guys that information here, definite integral. And I'm running out of space here. And like I said, over here we have this thing called a Riemann sum. If I can. All right, you guys okay with this? Definite integral here. All righty. Now, you might say, why do you care about this so much, Mr. Judge, this whole notation of definite integral here? Because that gives you the exact area now. It's no longer approximate. It will now be what? Exact. Okay? So if I said to you guys now, this curve here, whatever that curve is, this area that they're talking about is going to be the integral from a to b fx what? Dx. This is the exact area. It's no longer approximate. Anyway. It's all right. You're okay. All I had to do was take that limit and goes to infinity, which means my delta goes to 0. Yeah, it's gone. It's no longer approximate. It's now what? Equal. That's called, by definition, a definite integral. So you might even now say to me, okay, how do I use that? Well, you're going to have something called the what? I'm going to give it to you guys in words today. It's called the fundamental theorem of what? Calculus. And I'm going to give you really what's known as part 2. I cut to the chase. Okay? It's going to be the part 2. Fundamental theorem of what? Calculus. There's a part 1. I can give it to you as well, but I start with part 2 because it's, of course we could do a lot of other small details that make you believe in this, but I don't even think it's really that necessary. But okay. Let me find it. Okay. And I'm going to prove it to you guys. I have a video that you guys can watch for the proof of that. So here's the deal. You require f to be what? Continuous over the interval AB. Okay? And then you say, if you have that, then the definite integral notation we just gave you guys equals f of b minus what? F of a. Where big F of x is the what? Anti what? Derivative of f. Okay, so let me do something here for you guys now. Here's your definite integral, right? See this here, definite integral? Here's my f. What is this? F is the anti what? Derivative of little f. So if you know how to get an antiderivative, good for you. If you don't, come back next semester. And I've been warning you, and I've been telling you, and I've been preaching, and not everybody believes me. And they go, I'm just going to start my homework now, Mr. Judge. And I say, okay, good luck to you. No big deal. This is the fundamental theorem of calculus. Now you might say, what is this A and B here, right? Well, A and B, they're called limits. And A is what's called the lower limit of the integral, and this is called the upper limit. So it's kind of simple in a sense, because you said, did you set the table with all of this stuff? I did. I'm going to find my website in the second computer I have to use all the time. So we've set the table because we have worked with antiderivatives. Is that true? And I have begged people, go do your antiderivatives. All right. Numerical approximation. Okay, let me go show you guys here something. So when you go back to my website here, okay, and I'll probably send it to you even as an announcement. These are the videos here, right? This is the fundamental theorem of calculus. This is the proof that I'm talking about here. Okay, I even have this. Oh, I have it in my notes. Where is it in my notes? Where is that thing? I'm going to have to find it. It's a nice proof for you guys. I'll put it here. All right. So I have a nice proof there online in YouTube. I go through it. I got to find it. I go through the fundamental theorem of calculus, part 2. Prove it to people. There you go. I I got to get that worksheet here. I got to find that. Note to self. Okay. And then I go to what? Definite integrals here. And I have that worksheet for you guys in my website as well. So, ladies and gentlemen, here we go. There it is. And there it is. So I even have a whole bunch of videos with this stuff going through in depth, going through this process. And you say, where are these examples? They're right here. Wow. You just went through so many examples for me as well? Yes, I did. Yes, wow. Amazing. Examples from that worksheet. Oops, I don't want to go there. Okay. So it's there, ladies and gentlemen. So you now say, well, can you please go through some examples with me here and now? Sure. Let's give you guys a simple example here, okay? Let's say 0 to 4. I don't know, maybe just simply x squared dx. So that you can actually see here how what we've been doing is important. So, I mean, I could go to Desmos. Where's Desmos? Y equals x squared, blue. Okay? And then I'll say x equals 0. Okay, x equals what? 4. And let's put these are going to be our lower limits. And okay. And just for fun, we're going to bring that in here. I'm going to add to definite integral. Just so you guys can see this here. So here's what I want you guys to notice. This line here for the lower limit, that's x is 0 over here. Okay? It's going to be that vertical line. And over here is going to be the line x is 4. So this is going to be the area under that curve here between 0 and 4. And that's really what they're looking for. It's no longer approximate. It's what? It's exact. Now, if you guys have been doing your homework, you're going to have to simply tell me, what's the antiderivative of x squared? Uh-oh. Right? You might say, I know the family is going to be what? 1/3 x cubed. Is that true? This is what you're looking for. Easy peasy lemon squeezy. However, you might say, I have these limits now. What does this mean here, right? That the answer is going to be, yes, big F of 4 minus big F of 0 by the what? Fundamental theorem of calculus part 2. Proof in the video for 15 minutes. You can watch that, right? I'll send that as even as an attachment. So this is all based on whether or not you guys can find antiderivatives, and hopefully that's the case. But it's a little bit more than that. You say, why is that more? Because you're going to have to now do what? Plug in the upper limit of 4 and plug in the upper limit of 0. In other words, you guys have some work to do here, some arithmetic. Okay, you have arithmetic to do. So what is the antiderivative evaluated at what? At 4, the upper limit. It's 1/3 4 cubed plus c, which will really be what? 64/3 plus c. And then what's the antiderivative evaluated at 0? Well, that's 1/3 0 cubed plus c, which will really be what? C. Okay, so we're going to take those two values here. Say what two values? You're going to take these two. This, what else? And this. I guess I have to be consistent. I'm going to say here's f of 0. Okay. Yeah, can't draw a circle. So take that difference. You go, what's that difference? It's going to be 64/3 plus c minus what? C. And what does that give you? 64 what? Thirds plus c minus c. So, ladies and gentlemen, your final answer is simply just what? 64/3, really. So, if you really said to me, hey, Mr. Judge, how many new things are we going to do? It's a very philosophical kind of question. Assuming you already knew what to do. Assuming you know how to do some derivatives, assuming you know how to do arithmetic, I would say nothing really new, but other than saying, here's your fundamental theorem of calculus, watch the proof later when you get a chance. It's an amazing proof. I can't even find that worksheet. I'll look for it. I should have it on my website somewhere. But it depends on what you already know, what you've already done. So, ladies and gentlemen, I always say it's kind of downhill, but like I said, for some people this is uphill because they haven't done homework, or they haven't, they didn't take the Thanksgiving advice to master your antiderivatives. That's it. So if you know how to get an antiderivative, you're very happy. And that's all. What do you guys think? Was that simple? And that's powerful because it's really the area under the curve. It's exact. It's not even approximate. It's exact. And, maybe we should see the proof sometimes ourselves and go through it. It's an amazing proof. I mean, it's one of my favorite all-time proofs. This is why I made a video of that, and I put it online to, the whole world. And now, like I said, I think it's just about having you guys see a lot of different examples. And I went crazy one year, and I did a whole bunch of what? Just did a whole bunch of examples on a worksheet and drew all these pictures. Okay, anybody have any questions on that? So let's see some examples. Yes. Yeah. Yeah, good question. You remember that delta x that we had? Remember this was delta x? When you take that limit as n goes to infinity, your notation-wise is going to be now the dx here. So this is actually related to the fundamental theorem of calculus part 1 as well. So maybe we'll kind of read through that when I find that worksheet for you. But that dx is now going to be in place of the delta x. So yeah, let me go back here. Where is it? What do we have here? Maybe I did this? No. Here it is. See this doubt? See this here is the question here. You go, Mr. Judge, what happened to that dx? Well, it's the delta x. That's going to be your dx. And then here you have your f, and there's your f. This whole portion here, the limit with your summation, becomes the what? The integral sign. And all because you're taking n going to be arbitrarily large now, number of partitions. And this is called the definite integral. Yes, you need your function to be continuous. And that's part of the proof in the fundamental theorem of calculus. So I think all you have to do in some ways is see a whole bunch of what? Examples. And then this is a real, very simple example. You know, in Desmos, you know, and this, they'll change this one to be, let's delete that. We'll say -1 to what? To 1 even. And then you might say, whoa, let's think about this one. I'm going to talk a little bit about this. So let's take a look, right? They want to know, remember, this is a graph of y equals x right here. And then the limits, you got a lower limit being what? -1, okay? So you're going to have that vertical line. +1. This is the curve in purple. Y is x, okay? Right in here. So this is your y function. And then, if you said, you're really having me get the what? This area, right? And it's really the net area. We're going to talk about that. You say net area, yeah. So, by the fundamental theorem of calculus, this is the antiderivative evaluated at 1 minus the antiderivative evaluated at -1, okay? You guys with me on this one? You guys see the point? Easy peasy lemon squeezy? Okay. So if I said to you guys, we need the antiderivative of just x. What's that antiderivative? Do you guys happen to know what that is? Isn't that 1/2 x squared plus c? Didn't you guys use power rule there? All right. Now I have to evaluate that at 1 and -1. So this will be, I kind of write it all together here so you guys can see that here, right? 1/2 1 squared plus c minus 1/2 -1 squared plus c. Because we're plugging in the limits. You have a lower limit and an upper limit. Okay, you guys okay with that? So you get to do your arithmetic now. So you say, what's the arithmetic? It's going to be what? 1/2 plus c minus what? 1/2 minus c. Don't you distribute over here? Some arithmetic. So what's 1/2 plus 1/2? Oops. Sorry, not 1/2. I know 1/2 plus 1/2 is 1. But what's 1/2 minus 1/2? 0. What's c minus c? So you say, Mr. Judge, the area under the curve is 0 here? Go, that's crazy. How could that be? Did you guys see the picture? Do you guys happen to know why that is? Let's go back to this important piece. You see, remember we have that approximating rectangle. You guys remember that one? Remember this? So we had that approximating rectangle. The area under that portion is what? It's going to be positive. Does anybody happen to know why? Because you had the length, you had the width. That was the delta x. Remember that? And how did you get length? The length was really that height. You guys remember? So it was f of maybe x asterisk, that special point, which is really a y value. It's above the x-axis. Over here, I painted it red, a different color. You say, why? Well, the same kind of thing. It's a different point, but I would say, what do you guys notice now about that particular y value? It's still length and width. Anybody notice anything? The length is now negative. Why would the length be negative? It's below the x-axis. It's where the negative y values live. So what this is known as, if you said, Mr. Judge, should I cover all, do you want to cover all those sections where I have to kind of play with these area formulas? Where the area here of a triangle here is 1/2 base times height, and it's positive. And then the area here is going to be 1/2 base times height, and it's negative because the height's negative. And this is now going to be symmetric. You have an equal amount of area in blue, which is positive, and the area in red is negative. And so you're going to get that to be 0. This is a net sum. So any area above your x-axis is positive. And any area below the x-axis is what? Negative. And you say, why? Because the approximating rectangle will give you a negative length. You go, really? Why? Why is that a negative length? Because remember how you got it. It was the y coordinate for your what? For your height. The length. And if it's below, it's negative. If it's above, it's what? Positive. All the y values above the x-axis are positive, and all the y values below are negative. So they're equal and opposite area values. I just want to share that with you guys. Okay? Was that easy peasy? You might say, I don't believe you. Well, how about if I said, can you integrate sort of pi cosine? You say integrate? Yes. Oh my Lord. Let's find out what this is. Does anybody know it's going to be the antiderivative of the function evaluated at pi minus the antiderivative evaluated at 0. Here are your what? Limits. Do you guys know what the antiderivative of cosine is? So this is going to be what here? We can just simply write, we can forget about the c. Sine pi minus sine of what? 0. You might say, where's your c? Well, it's going to cancel, so I don't put it down anyway. Can I do that if I'm a little OCD? I could. And that's what I used to do until I see my c's go away all the time. I go, okay, I don't have to do it. However, what in the world is sine pi? What's sine 0? So you're going to say, is that 0 minus 0? It is. So the area under the curve is 0 for cosine from 0 to what? Pi Well, let's ask Desmos. If your curve now is what? Cosine. There it is. And then we want to go now from what? 0 to what? Pi. Okay, I'm going to bring it in. There we go. What do we know? This is from 0 to pi, is that right? Remember, this is that line, x is 0 over here. And over here, you have the line, x is what? Pi. Anybody know? Isn't that pi over 2? What do we remember here? The area in blue with this approximating rectangle. That's a big deal. That area is what? Positive. Is that true? Any area above the x-axis is positive. What about the area below? What's going on there? That approximating rectangle is what? What is that? That's negative. So the area is equal but opposite. Anything below is going to have a negative area. And you say, why? Because remember how you got the length? That length here, this is still delta x, but the length is f of what? X asterisk. That's a y value. All of those values of y below the x-axis are negative. Similarly, I'll say it again, right? This length, L, is the same f of x asterisk, and it's positive. So maybe I'll just put it that way, greater than 0 and what? Less than 0, and I color the area there below the x-axis red for negative area, and blue for positive area. And there's that symmetry really from 0 to what? Pi. Right in the middle, you have pi over 2. And that's because you're looking at the cosine curve. So really, if you said, what if you gave me this question now instead? Divide that by 2 instead. Okay. What do you think's going to happen? Right? Let's put pi over 2 instead. Do you know what sine pi over 2 is? What's that number? 1. Okay, so this is now going to be 1 minus 0, which is what? 1. And let's see if that makes sense. We're saying from here to here, ladies and gentlemen, this area here is what? 1. Just so you guys know, that's from 0 to pi over 2. It's positive 1. Now, what does that actually mean about this portion? This portion over here is what? It's negative 1. So negative pi over 2 to pi, that's negative 1. All because you know what? I've been using the green. What's this? Anti what? Aren't you guys happy you did this over Thanksgiving? You go, oh my God, Mr. Judge, thank you so much for warning me. Huh? I'm serious. I don't. I tell you guys the same things I tell my own children. I don't. I can't. People I love. What if they give you an easier one, like a constant? You go, oh my God. -2 to 5, and then they give you like a constant 4 dx. All right? What do you think you guys do with this? You said, is that still the antiderivative function? And it is? Okay, you guys see what I'm saying? What's the antiderivative of 4? It's 4x. So let me show you some other notation that I use. Yes, it's 4x plus c. But sometimes they're going to use notation this way, okay? Sometimes that's actually a little bit more convenient here, where this big F is still the what? Antiderivative of f, and you are still doing what? Evaluating this portion here, 5 and what? -2. So just giving you some extra notation here. So you just now have to do some arithmetic. You say, is this going to be 4 times 5 minus 4 times -2? And the answer is yes. That's 20 minus a -8, which is 20 plus 8, right? And what does that give you? 28. Okay. See all the detail? -2 and 5, and that's a constant function. What did I give you? 4. What happened here? Change that color to, I don't know, blue. Okay, let's show you guys these details. Right? You might even say, well, what's going on here? Well, here's the function. The constant function. Okay, so you say, what does that graph look like? It looks like this. What is this? There's a 4. Now, what are the limits? X is -2, X is +5. You guys okay with that? Notice that curve is all above the x-axis. So if you had to find the area here, what's the deal? Isn't that a rectangle? What's the length? 5 minus -2, which is 7. But you guys remember, here's 5, and here's what? Isn't the length always the right value minus the left value? Okay, that's something we're going to use, some common sense. The right value minus the left value will be 7. And then what's your height here? Or your width? See that 4 and 0? So also, this is going to be what? 4, by the way, and 0. So your width. 4 minus 0 is what? 4. Isn't it true? 7 times 4 is what? 28? You guys okay with this? And that's what we did. This is what you can do from geometry for some questions, not every question. And so there's sections in the book that says, hey, I want you guys to do a whole bunch of geometry area questions. Okay. Is it necessary? Well, not really, but it's an assumption. It's an assumption people know about area, about rectangles, area about triangles even. You can go straight to your antiderivatives and say, do some arithmetic and antiderivatives. So that's what I choose to do. And there it is, ladies and gentlemen, the same exact kind of question. But, you know, calculus is like the generalization of geometry in some ways. Because you don't have to have, you can even do this with what? Curves that you don't have geometric formulas for. That's why I say the generalization. You don't have a formula for these curves and these areas. That's the power of calculus. There's no formula there. It's not a triangle. It's not a trapezoid. It's not a circle. It's not a square. That doesn't even have a name other than area between 0 and pi for the cosine curve. That's it. You know, here we have triangles, by the way. And then the one fundamental question that they also give you here, and this is going to be kind of fun. These are all basic questions here. They said, what's this from -1 to maybe 3 of the absolute value? Okay? So this one's a little bit fun. You go, what do you mean by fun? Well, here's what I mean by fun. You have a problem. Do you guys have an antiderivative formula for the absolute value? There's no antiderivative formula. So you say, what do we do since there's no antiderivative? Well, if there's no antiderivative, here's what you guys do. You have to remember, what's the definition of this what? Of this function. You have a piecewise function. It is x when x is greater than or equal to 0. It is opposite x when x is less than 0. So we're going to use this definition, okay? And you're also going to use this fact. It's probably one of the most important facts when dealing with antiderivatives or integrals. Here's a fact. Of course, your function f is continuous over AB. It's a very, very useful what? And then I'm going to say let C be in that interval AB. It's not at the endpoint. That's why they put the open interval. C is another constant, okay? And so what they say here is this. If you're going to integrate or find the area over that whole interval AB, you can integrate from A to C and then from C to what? B. Now, it turns out this is kind of easy to visualize. Here's what I want you guys to see and to know. They're taking any c in that interval. There it is. Here's c. You may have a lower limit value of a. It's still a lower limit. That doesn't change. You have an upper limit value of b. That doesn't change here. So c is in that interval. All right, you guys okay with that? There's a picture if you want to see a picture. And I might have those notes somewhere if I dig them out, but here's kind of the idea. Here's A, here's what? B. Now take any C, it doesn't matter where it is. Here's C. What they are saying is the area in blue here, the blue integral, is the same as this green integral here, plus the orange integral, okay? Where the green integral is from A to C, and then the what? The orange integral is from C to B. Isn't that kind of interesting? This is all about area, working with that area here. So you might say, how does that help me with this question? Do you see how this helps? Let's take a look. What do you guys know? You have two functions. Here's your green, here's your what? Orange. Your C value is 0. So what you can do here, I'm going to kind of write it up here since I have all the information here, okay? You can integrate from -1 to 0. What do you guys know about -1 to 0? What function is that? Right? For negative values, the function's negative x. You guys okay with that? For positive values, your function's now what? X. So that goes from 0 to what? To 3. So this integral that they gave you here can be done piecewise. And that's kind of the lesson here. Copy that and I'll paste this here. So the price you pay is 2 integrals. Okay, you guys with me on that? Let me do everything in orange here now. What's the antiderivative of negative x? That's -1/2 what? X squared. You evaluate this from x is -1 to x equals 0 here. Okay, so if you know antiderivatives, you know that portion there. What about the green? This is now plus what? 1/2 x squared evaluated from x equals 0 to what now? 3. So I'm using the piecewise definition. The first one is when your values of x are negative, and then the second one is when the values of x are positive. That's how we handle that. Okay, so let's do some arithmetic. Then that's going to be, what's that going to be here? -1/2 0 squared minus -1/2 -1 squared. Okay? And over here, this is plus what? 1/2 3 squared minus 1/2 0 squared. And let's make sure my parentheses are appropriate. Okay? You might say, why do you have extra parentheses on the other one? Because of the negative sign. Now, this portion goes to 0. This is negative 1/2, right? So let's be careful. You got negative 1/2 down here. Plus, this is plus. Plus really what? 9/2, because this portion over here is what? 0. So negative minus a minus makes that a plus. Final answer, ladies and gentlemen, this is 10/2, or really what? 5. So the area here equals what? 5 here. Okay, you guys okay with this one? All right, then what they can give you is questions that kind of look scary. Oh, come on, let's get the... So they give you x, square root of x, from 1 to 4. And you might say, I don't even know how to do that. Well, yes, you do. You guys know why? You know about antiderivatives. Use a little bit of that algebra. Isn't this x to the 1/2? What's this? This question is really going to be the integral of x to the what? 3/2? Okay? I need the antiderivative of that, evaluated from x is 1 to x is 4. So what's the antiderivative? Isn't it x to the 5/2 over 5/2 from x is 1 to x is 4? Is that true? Which is 2 what? 5ths x squared square root of x. Is that right? Double check. Didn't we do those? Isn't 5/2 2.5? So you say, what does this become? Well, this is 2 5ths. 4 squared square root of 4 minus 2 5ths 1 squared square root of 1. And this portion over here, square root of 4 and square root of 1, we know what those things are. This will be what? 2, and this will be what? 1. So you get 2 5ths times what? 16 times 2 minus 2 5ths times 1. I think it's 64 5ths minus 2 5ths. Double check my arithmetic. I figured out my wife has only been giving me 1 cup of coffee. I know, and it's probably decaf. She's sneaking that in. You know what I mean? So all these mornings, I'm like, how come I'm not even awake and I don't even know my name? It's because she's only been giving me 1 cup in that little thing, and it's probably even decaf, knowing her. She's sneaking that in. That's right. She's taking care of me, and it's making me angry because I'm making mistakes and I'm not even awake. It all depends on how much REM sleep I get. What do you guys think? Is that one pretty simple? Should we do a tough one? One for the road? See, what do they give me? 3 minus x dx from 1 to 5 now. All right, let's do 1 to 2. It's okay. Okay? we need, again, the antiderivative of 3 minus x. What's that antiderivative? Isn't that 3x minus 1/2 what? X squared. We evaluate that from x is 1 to x is what? 2. So if you guys worked on those antiderivatives, you're already there. This is that big F. So f of 2 minus f of what? 1. 3 times 2 minus what? 1/2 2 squared, and then 3 times 1 minus 1/2 1 squared. Sometimes it's easier to do it a little bit like this. Right? Maybe you see it better. All right, you guys see my point? You got to get that antiderivative function. So let's do some arithmetic. This is going to be what? 6. I think that would be 1/2 times 4 is 2. 6 minus 2. Minus 3 minus what? 1/2 will give you 4 minus, what's this going to be? You might have to do some arithmetic. 6 halves minus 1/2, which will be what? 4 minus 5 halves times 2 times 2. And that gives you 8 halves minus 5 halves, which is really what? 3 halves. All right, you guys good with that one? Is that easy peasy lemon squeezy? All right, well, of course I did go crazy with some of these here. Like I said, I really, man, there's more to do. We'll try to do some more tomorrow. But you know, what I'm saying here is if you said to me, go here. You see this here? Definite integral and area under the curve. I'm going to assign this for homework. What's the good news? You have all the what? Solutions. And let's integrate. Let's work on some what? Integration. What do you guys think? So I'm going to move this down here. Let's start to talk about these here. These are called we worked on these yesterday. Is that right? Let me look at my website. Definite integrals. How do you actually answer the question? Do you guys remember? What's your answer here? By the fundamental theorem of calculus part 2, it's the antiderivative evaluated at x equals 1 and x equals 8. So what I'm not going to do is graph every one of these here, okay? So this is by the fundamental theorem of calculus part 2. Is that right? So remember what I said. You need antiderivatives. What's the antiderivative there of x to the 2/3 power? What do you guys use again? Do you guys remember? Power rule. Add 1 to the power. But you got to know how to add a whole number with a fraction. Convert to what? 1 is 3/3. So this is going to be what? X to the 5/3 divided by 5/3. And you guys know, just write the reciprocal. That's 3/5. X to the what? 5/3. Evaluated from x equals 1 to x equals 8. So here's your anti-what derivative? Okay, did you guys look at some of those videos I put there for these extra examples? Like 30 examples? More. more. So notice this. Isn't this the antiderivative? Yeah. All right. Now, here's the rest of it, though. You say, well, how do I evaluate this stuff? Well, plug that in here. You're going to start to do some arithmetic with this, okay? So now you say, okay, 3/5, 8 to the 5/3 power minus 3/5, 1 to the 5/3 power. So go back and again, remember, base to the m over n power. Oh, what do you guys want to do? That's the base to the 1 over n to the m, which is really the nth root of the base. Okay, use a little bit of your algebra here. And I'm actually going to factor out. Okay, I'm going to factor that part out. Now, this portion becomes really what? This is 3/5 now. Isn't this going to be 2 to the 5th power minus 1? I believe so. Because the cube root of 8 is 2, and then that's 2 to the 5th. Is that right? And then that'll be 32 minus 1, which is 31. So it's 3/5 times 31, 93/5. So I won't graph them today. These are all continuous functions over the interval. And there you guys go. This is what you guys will have to do, right? This is a pretty fundamental integration kind of question. And, and I might even change a little bit of that study guide or final exam test, so just kind of be aware of that, and I'll let you guys know if there's something that stands out that I say, oh, I really wish I did this better, but who knows. Number 2, let's go through something like this. This is an important detail for these integrals. Right, so number 2 here, ladies and gentlemen, I want to say something about this. Remember, this is your function f here, right? Your function f, which is 1 over x squared, needs to be continuous over the interval from 1 to 4. Is it? The answer is yes. Because even though you can't have x be 0, if you guys remember that. So it's okay. You're integrating over 1 to 4. So this is something, again, that's an important detail that people really overlook. In Calculus 2, guess what you get to do? You get to integrate all over again, but this time it's over a non-continuous function. So these are very specially chosen where this is gonna happen, okay? Just so you guys know, Calculus 1, we don't worry about, they're going to give you where the function is going to be continuous. Calculus 2, not necessarily. Just to kind of throw that out there, right? This interval is you have a rational function, has a vertical asymptote at the origin, but your interval doesn't go over through the origin. So it's a Calculus 1 question. Okay. So now, again, this is x to the minus 2. All right, you guys okay with that? And then that's going to be antiderivative. If you want, I'll just change notations. You say, Mr. Judge, isn't that big F of 4 minus big F of 1 by the fundamental theorem of calculus part 2? And the answer is yes. But you need the antiderivative. Now, what is the antiderivative of x to the minus 2? Well, you simply use power rule again. And that's x to the minus 1 over minus 1, or it's minus 1 over x. This is the antiderivative, right? And yes, again, if you are still getting up to that speed, it's negative 1 over x plus c. So we're going to have to evaluate negative 1 over x. The lower limit is 1. The upper limit is 4. So I would say be very careful here, okay? This is where you can really make a mistake. All right? Antiderivative, I don't know, maybe we'll say Plug in the 4 here. Plug in the 1 over here. Make sure there's a what here? A difference. So just be careful with that arithmetic, because that's where people will definitely make a mistake. So this is negative 1/4 plus 1, or 1 minus 1/4. Final answer will be what? 3/4. There you go. What do you guys think? Easy peasy lemon squeezy? Not too bad. Is that right? Okay. These are some I just kind of wrote down. Let me do this number 3 here. And let me remark about something here. Let me give you a few facts here about integrals, okay? Let me give you an example. And I'm going to write this as what's called indefinite integrals. You might say, what's an indefinite integral as opposed to a definite integral? Well, if you don't have any limits. So if I said to you, notice this. This is indefinite. Indefinite means there's no what? Limits. And it doesn't matter if I give you a definite or an indefinite, but maybe in terms of the properties, I just want to write it down that way as an indefinite, okay? A couple of things that people say about indefinite integrals. So here's some facts, right? Let me just say I'm going to divert here. But nevertheless, here's your first fact. If you have to integrate a sum of two functions, well, the integral of a sum is sum of integrals. That's really an important detail as well. Okay, so the integral of a sum is sum of integrals. The integral of a difference is going to be what? Difference of integrals. And then the third fact, we'll say the integral of a constant times a function, well, you can pull out the what? The constant. And then maybe the fourth fact, the integral of a constant, just a constant, is cx plus, and then that's a big C if you want to think of it that way, because this is an antiderivative. So very often they will give you these properties here of integrals. Okay, I just want to kind of let you guys know that that happens as well, and I'll show you how you use the properties. And yeah, maybe I'll just label that here properties here, okay? So you say, why did you give that to me here, these properties? Well, whether it's a definite or indefinite integral, all those same properties apply. If I wanted to use properties now, I have a sum here. So you say, can I just integrate x squared and then integrate that constant 1 dx, which is just really going to be 1 times anything is itself. Okay? And you might say, why are you writing this down this way as indefinite? I was given a definite integral where I have a lower limit and an upper limit. Well, we can do that for the time being. And so now it might be easier for some, for this first integral, get the antiderivative. Isn't that 1/3 x cubed? And maybe I have to colorize these two. So you guys can say, hey, you got that first derivative. Sorry, first integral. And isn't this the antiderivative? And then by properties, what happened? This is plus what? X. Because we just integrated that x. And then you say, do I just put plus a c? Yeah, you can put plus c, constant. And that's the same as if I try to say to you guys, can you give me the antiderivative here? Remember that? So it's the same exact antiderivative. Okay, you guys understand? I just gave you properties now of integrals instead. So you can take these antiderivatives separately. That's all they're saying. Take them separately. But then you say, what about my limits? Okay. Then if they gave you limits, then apply the limits from 0 to what? 2. This is going to be that big F. That's the same. Would you guys agree? Same family, antiderivative. They gave you x squared plus x. So then you say, well, what is this going to be now? So we say, okay, big F of 2 minus big F of what? 0. Purple and what? Pink. So you got your purple and you have your what? Pink. So just do your arithmetic. 1/3, 2 to the third, plus 2. You say, can I put my c? Okay, but it's going to cancel. Is that right? 1/3, 0 cubed plus 0 plus the same c. So this will be 8/3 plus 2 plus c minus, really minus c, because you have 0 here and you have 0 over here. Is that right? So you're going to get really 8/3 plus that 2 over 1. And so you get what? 8/3 plus 6/3. What's 8/3 plus 6/3? It's 14 what? 14/3. So I just wanted to share with you some of the properties here as well, because the properties are very useful, I think. But it's the same as what you've already done. If you had to get the antiderivative of x squared plus x, it's 1/3 x cubed plus x plus c. So anyway, just to let you guys know. What do you guys think? If you did the work on antiderivatives, you're really happy. And then, like I said, I kind of kicked it up a little bit here. Let's bring some of these down here. And I'm going to bring this one down. We'll call that one number 4, I guess, right? Okay, so if you want to use the properties again, I mean, I can bring along what? The limits. There's nothing wrong with that. I can do that too. Okay? And then I can pull out that constant. Okay, didn't I use the properties? The integral of a difference is going to be difference of what? There's a difference. Integral of a constant times a function. Pull out the what? Constant. And then now you might say, do I have to integrate just x? Yes. Do I have to integrate x squared? Yes. Do I need to put the 2 times that constant? I'm sorry, times the antiderivative? I do. Here's my point, right? Here's the deal. Just with properties. What's the antiderivative of x? It's 1/2 x squared. Is that true? And then minus, what's the antiderivative of x squared? 1/3 x cubed. Should I put my c? No, just put your limits. You guys okay with that? So just put your limits. You don't have to put the what? The c there. Okay? Now, I can simplify this because 2 times 1/2, that's just going to be x squared minus 1/3 x cubed. Evaluate that from 0 to 1. So, ladies and gentlemen, you may appreciate these properties I just gave you here because they do make your life a little bit, in terms of notation, easier maybe. I don't know. And now you just plug in the limits. Is that right? Because this is that, again, big F, the antiderivative. So this will be f of 1 minus f of 0 All right, you guys okay with that? So we get what? 1 squared, be careful here, minus 1/3 1 cubed. This is the big F of 1. Minus 0 squared minus 1/3 0 cubed. So let me emphasize. Here's the 1, here's the 1, here's the 0, here's the 0. And so really, I think if there's mistakes, sometimes the mistakes are in the arithmetic. So you get 1 minus 1/3, right? Minus really 0, which is 1 minus 1/3. Okay. Replace the 1 with what? 3/3, and ladies and gentlemen, you get what? 2/3. So there you go, easy peasy lemon squeezy. Is that pretty good? Just using properties? Yeah, I think, I can rewrite it and, I'll do this one here. This is going to be an interesting one, yeah. So this is why I wanted to bring out those properties here. Okay, so we can try this one with just properties. Integral of a sum is sum of integrals. Integral of a difference is difference of integrals. So take a look. I did the first 2 properties here. Okay. And now maybe I just want to take out the what? All the constants now. So it's 2 integral x squared dx minus 4 integral x dx plus 5 integral dx. So maybe I'll call that, no, we don't want to use green. Maybe purple. Orange, pink. Sorry. Okay, so let's get these antiderivatives, but just don't forget you have all the constants everywhere, right? So what's the antiderivative of x squared? 1/3 x cubed, is that right? What's the antiderivative of x? 1/2 x squared. And the antiderivative of just this, you may want to write a formula down. You might say, isn't that just 1? Well, that's just going to be what? X. So maybe you want to just write this down here. The integral of dx is just x in general plus that c, written as an indefinite integral. Okay, so that one very much shows up a lot in your life. So that's why I put that as a separate fact. It shows up often. Okay, so don't forget you have what? The constants, okay? So I'm going to put that here. And then now all together, you could just simplify. You say 2/3 now, right? X cubed minus, this will be 2x squared plus 5x. We evaluate that from x is -1, x is +1. Okay? And this whole thing is at what? Isn't that big F? All right. So this will be f of 1 minus f of -1. All right, ladies and gentlemen, just be careful here. I'm going to kind of recommend, like I said, we don't want to make a mistake. So I know when I make my mistakes, I know I'm going to do it this way. This will be minus now, so be careful here. Minus 2/3 -1 cubed minus 2 times -1 squared plus 5 times -1. So notice all the detail that you sometimes have to do. Here's my first limit of +1, the upper limit. The lower limit is -1. And don't forget, this has to be subtraction here. So you may have to use 2 lines. I got to use 2 lines here. Okay, you guys okay with that? So the good news, at least for me here looking at this, is I like 1 because 1 cubed is 1, 1 squared is 1. Okay, but just be careful with the negatives there. So I'm going to keep this first portion in parentheses. So I kind of try to keep them in parentheses as long as possible. 2/3 minus 2 plus 5, and then minus 2/3 times a -1, is that true? Minus 2 times a +1, and then 5 times -1 is -5. So just be careful with the arithmetic with those negative numbers as well. -1 is still kind of nice. And then I'll keep that 2/3 in parentheses. Looks like 2/3 plus 3. Now minus -2/3 minus 2 minus 5. Isn't that just -7? You guys okay with that? And then I'm going to distribute. I'll get rid of the second set of parentheses. So distribute here. And so we get 2/3 plus 2/3 will give us what? 4/3. 3 plus 7 is plus 10. And then you could just multiply top and bottom by what? 3. So you get 4/3 plus 30/3 will give you what? 34/3. And there you go. Easy peasy lemon what? Squeezy. So there is danger when dealing with this arithmetic, no doubt. No doubt. You got to practice that arithmetic and adding fractions and whole numbers. It happens a lot, especially with polynomials. Those polynomials, you'll get that all the time. All right, you guys okay with that? Does that seem simple? And then you get the famous trig functions. But if you know your antiderivatives, should be okay. Okay, so sometimes, well, let's see, we can keep it as is. What's the antiderivative of secant squared? Tangent. Good. Good. Here's your antiderivative. Okay, so this would be f of what? Pi over 4 minus f of 0. So that's tangent of what? Pi over 4 minus tangent of what? 0. Do you guys know tangent pi over 4 is? 1. Tangent 0 is what? 0. So you get 1 minus 0, which will be what? 1. All right, you guys okay with that one? Isn't that pretty simple? So long as you know what an antiderivative is. And then, this is always everybody's favorite when you start dealing with absolute values. A lot of these absolute value curves, people go, wait a minute. I don't know, is that 6? I forget what number we're at. 5, I think that's 7. So that's 5. This will be what? 6, 7. So these absolute value functions, you got to be careful here. You got to use the definition, okay? Now, I'm going to write it this way. The definition of the absolute value of anything, you got to do it piecewise. It is that thing when that thing is greater than or equal to 0, or its opposite when that is negative. So what I mean by that is what's in this triangle here is really x minus 2. So the definition of that function is x minus 2 when x minus 2 is greater than or equal to 0, or opposite x minus 2 when x minus 2 is negative. This is your definition of a piecewise function. What you really have to do here is solve a simple linear inequality. Right? What do they mean by that? Do you guys know what x minus 2 being greater than 0 means? What does that even mean? That means x will be what? Greater than or equal to 2 if I add 2 to both sides, right? And the other one, if I add 2 to both sides, means x is less than 2. So this is kind of everybody's favorite, right? All those little details. And these aren't really that bad if you understand that they gave you a nice what? I gave you a piecewise function here. Whatever. Right in there, it's a piecewise function. But then the real problem is people say, well, what about the limits? You're going from -1 to 3 here. Is that right? So you're going to write this as a sum of two functions. This is really the first piece plus the what? second piece. There's two integrals. Now you say, how did you get that next one? Well, do the same distribute. This is negative x plus 2, or 2 minus x. This will make everything a little bit easier. Okay, so far so good. What's the c value I gave you guys? Remember this 2. This 2 is important. Okay, because what do you guys know about 2? 2 is in that interval. This interval that they have here is from -1 up to 3. Is that right? So how does the 2 fit? Well, from -1 up to 2, 2 up to 3. So that's what that interval is. So -1 up to 2. Which function is this one? See that? Which piece do I use for this? -1 up to 2. Oh, those are for values that are smaller than what, 2? Is that right? So we're going to use -1 up to 2. I guess I should have written it this way. -1 up to 2, you use 2 minus x dx. Okay, that piece. You say, why? Because that works for numbers that are smaller than 2. Numbers that are at least 2, we have to use the top piece. Maybe color that one orange. And that's going to be this from 2 to 3. So we'll say from 2 to 3 instead now. That's when we use x minus 2 dx. So you have the green and the orange. That was that property I gave you guys yesterday. Right? You can split up an integral when you actually go from what? Well, whenever you have to. You could do it all the time, but you only do it when you really need to. Here you need to because you have a function defined piecewise. That absolute value is a piecewise function. All right, so anybody have any questions on that part? That's a real popular question. Students always have questions on those absolute values. Even my daughter, when she was doing her calculus homework, I remember would come home and say, how do you do these, right? And I'd have to show her this definition like I'm showing you guys. So what's this integral, this first one here, right? You now have 2 different integrals now. So this will be what? 2x minus 1/2 x squared. Evaluate it from -1 to 2 plus there 1/2 x squared minus 2x. Evaluated from x is 2 to x is 3. So this integral. And then what? This. Notice again you have what here? Plus. Plus. Okay, you guys okay with that? Just be careful with your what? F of 2 minus f of -1. Over here, this will be f of 3 minus f of 2, and they're different f's. These guys, they're different antiderivatives. So, okay, 2 times 2 minus 1/2 2 squared here. Minus, be very careful, 2 times -1 minus 1/2 -1 squared. This is the one on the left. The one on the right, I have space. This is where I notice I make mistakes. And don't forget, you're going to add those here. Is that right? You add these here. So Just to go through all the details, the devil's in the details. So let me double check here. 2 times 2. Let's double check with our colors here, okay? Because this might be helpful, right? So just be very, very careful here, ladies and gentlemen. It's always where the arithmetic comes in. Okay. So we get what? 4 minus 1/2 times 4 is 2. I'll put it down here. Minus -2 minus 1/2 plus 9/2 minus 6 minus 1/2 times 4 is 2. 2 times 2, that's minus 4. Okay? So I just want to share with you guys here. Let's do some arithmetic. 2 plus 2 plus 1/2, it looks like over here. Double check. 9/2 minus 6 still. You know what I can do? That'll be just plus 2, right? 2 minus 4 is -2. The opposite is positive. So now I can get rid of all my parentheses. I get 4 plus 1/2 plus 9/2 minus 4, it looks like, right? -6 plus 2. 4 minus 4, then 1/2 plus 9/2, isn't that going to be 10/2? But they're known as what? 5. Anyway, just be careful with the arithmetic. Applying those limits can be a what? Can be a challenge. All right. All right, let's try this one here. This was let's do number 8 here. We want to make up an 8 here. We got to integrate 2 sine theta minus 4 from 0 to 2 pi. And then they'll put a nice d theta here for you. Okay? So we're going to use properties here. Okay, you guys okay with that? So what's the integral of a difference again? Difference of what? Integrals. Can I pull out the constants? Yes, pull out constants. Okay? So you're going to get now 2 sine theta d theta minus 4. Oh, didn't I say that shows up a lot? Okay. That shows up a lot. Okay. So what's the antiderivative of sine? Outstanding. Negative cosine. You guys see how you have to know those things? What's that integral of theta or d theta? I gave you the answer. It's just theta. So combine your constants now. That's -2 cosine of theta minus 4 theta, right? Your constants there. We don't have to highlight them anymore, but they gave you limits. What were the limits? From 0 to what? Pi. Lower limit is 0, upper limit is pi. And So altogether, really, this is that antiderivative. So just like before, it's big F of theta, theta 0, theta pi, right? So this is big F of pi minus big F of theta. So be careful. Negative 2 cosine pi minus 4 pi. So sometimes, again, I put it in parentheses. Minus negative 2 cosine of 0 minus 4 times 0. So maybe it's easier to see with colors. And then you got to remember some cosine. What is this? What's cosine pi? Anybody know what cosine pi is? Anybody have a good trig course? Anybody here take trig? You guys know what's cosine 0? 1. So negative 2 times negative 1 is positive 2 minus 4 pi minus, what's negative 2 times 1? Looks like it's negative 2. It's just negative 2 because this portion is 0. So I always keep these parentheses until the last second because I find it to be helpful. 4 minus 4 what? Pi. Okay, you guys okay with that one? Easy peasy lemon squeezy? What do you guys think? Is that okay? Anyway, let's give you some indefinite integrals. How's that? What do you guys think? You might say, how does everything work when they're indefinite? Same exact way. You just don't have any arithmetic to do at the end. So, you know, sometimes they'll give you this because it's good practice doing integration, getting antiderivatives. Or if you guys say, you know, I want to do some more practice, how would we go from negative pi to what? Pi. Doesn't matter to me. Let's use properties. What are your properties? Use your properties. And then sometimes students will say, can I just pull out, since I'm using properties, don't I just pull out the 2? So I can save at least a few steps, or at least save one step, pull out the constant 2. Sure, you can do that. You guys okay with that? And so then now it looks like you just have what here? I'm going to say this shows up a lot. Shows up. Shows up. What are all those antiderivatives? What's the antiderivative of theta? Isn't that 1/2 theta squared? What's the antiderivative of sine? What do you remember? Antiderivative of sine? Negative cosine. What's the antiderivative of cosine? So let me get out my colors so you can see everything here will be an antiderivative. And again, you evaluate this from what? Negative pi to pi. Okay, so this would be f of pi minus, bless you, f of minus pi. Okay. 1/2 pi squared minus cosine pi minus 2 sine of pi. This is going to be, in the parentheses, minus 1/2 minus pi squared minus cosine minus pi minus 2 sine of minus pi. I'll get out the colors if it makes it easier to see everything. I just have to remember what my cosine of these values are. What's cosine minus pi again? Is that -1? What's sine of pi? Isn't 0? Oh, cosine minus pi? Do you guys know anything about cosine? Cosine is nice and what? Odd. Is that true? What does that mean? This is cosine pi. This would be -1. Sine is even. What does that mean? What's minus sine pi? And that's still 0 because sine pi is 0. Anyway. (1/2 pi squared minus a -1). And that portion, -2 times 0 is 0, so I'm just not even going to write it down. And then minus 1/2 negative pi squared is going to be just what? Pi squared. And that's going to be minus a what? Is that minus a -1 again? And that portion is going to be 0. One half pi squared plus 1 here minus 1/2 pi squared plus 1 here. That whole area is 0? Really? Is that 0? Let's check something in Desmos. Theta plus sine theta minus 2 cosine theta. Sorry, where's Desmos? Y equals theta. Is that minus sine theta? Plus sine theta. And then minus 2 cosine theta? Okay. I'm going to do negative what? Pi. That's a very interesting curve. In fact, I could just even do it this way here. You know, I could even just restrict the domain. You know, see it that way. Doesn't look like it would be 0, but isn't that amazing? Doesn't even look like the area, the net area would be 0, does it? Anyway. But it does remind me of something, and I'm going to give this to you guys here. Let me give you guys a couple of also important details, some facts here, okay?
Professor,
Yeah.
on the right-hand side, shouldn't it be negative pi, not pi squared?
Let's see, do we screw that up? Negative pi? Where?
You see how it's 1/2 times negative pi squared?
Yeah.
The second set,
Yeah.
if you go a bit down, you scroll down,
Yeah.
you just plugged in pi squared instead of negative pi squared.
Well, negative pi square, you're talking here, right?
Yeah.
Well, you square the negative pi, and that gives is positive pi.
That's right.
Yeah, so it's still it's okay. Yeah, you know, just looking at that curve, it's kind of an interesting curve. But I'm going to give you guys a fact here that you guys, first of all, definition of what we call a symmetric interval. This really isn't happening here. Symmetric interval is like when you have from negative a to a. All right? So that's a symmetric interval. So you got two facts here. When you integrate, we'll say this. If your function f is even, and you integrate an even function, you know what you can do? This is double from 0 to a, that function. Okay, this is going to be a very useful fact. The simplest example I can give you guys, here's the simplest example. If they say, can you integrate from negative 1 to 1 a nice even function x squared, right? All right, what's an even function? Let me see, do I even have it right? Isn't that 1/3 what? X cubed. See this here? 1/3 1 cubed minus 1/3 negative 1 cubed. Let's see if we even have this correct. 1/3 plus 1/3, and that'll give you 2/3. Okay? So we know the answer is 2/3 here. Okay. But here's my point. You could have just said, let's integrate from 2 to 1. You're going to get 2 times 1/3 x cubed, evaluated from 0 to 1, which is 2/3 x cubed. 0 to 1, that's going to be 2/3 1 cubed minus 2/3 0 cubed. The answer is what? 2/3. So here's my point to you. What is very useful, the second, this is a lot easier to integrate. You say, why is it a lot easier? Anytime you have 0, what's the deal? It's easy to handle. So what I want to say to you guys, if you have an even function over a symmetric interval, okay, here's your symmetric interval from negative a to a, then it's a lot easier to integrate, just double the area.
Professor, what do you mean by even?
An even function? What's an even function? Let me go back. Let me erase this. Anybody remember trig? You guys skipped that course? Even functions? Huh? Well, is sine even or odd? I think sine's odd. Cosine's even. So you say, what's an even function? An even function is where you have f of minus x is f of x.
Odd.
So f, you have this, then we say f is what? Even. So this is actually an extremely important idea. The example I just gave you right now is the simplest even function you can think of, x squared, by the way. Now, compare that fact to the next fact. You say, here's fact 1. What's fact 2? Well, and this is something that happens too. And it's only over symmetric intervals, okay? So fact number 2, if your function is odd, and you're integrating over a symmetric interval, don't even bother. The area is 0. Now you might say, what does it mean for a function to be odd? If f of minus x is minus f of x, then f is what? Odd. So it's like, don't even bother. Now, what's the easiest odd function you guys can think of? Yep. So I'm going to integrate x cubed dx over negative 2 to 2. Don't bother. It's 0. You go, well, why? Well, isn't that 1/4 x to the 4th from negative 2 to 2, which will be 1/4 2 to the 4th minus 1/4 negative 2 to the 4th, which will be 1/4 2 to the 4th minus 1/4 2 to the 4th. You get 0, don't you? Is that right? And this is only applicable over what's the deal here? Negative 2 to 2. Symmetric intervals. You must have a symmetric interval here, which is why when I first looked at this, I said, oh my God, the area is 0. Did I give, I didn't intend to give like an odd function, really. And I don't even think this function's odd, by the way. It might be, but I don't think so. You say, how do you know? What's so important about even and odd functions? It's not even an odd function, but the area turned out to be 0 here. Do you guys know what's important about even and odd functions? Even function is symmetric about the what? The y-axis. An odd function is symmetric about what? Get rid of that. It's symmetric about what's called the origin, the x and y axis. And that's why this area under the curve, if you did x cubed from any symmetric interval, even if I kept negative pi to pi like this, there's an equal area under the curve to the right that's positive as to the left of that 0. You know, it's the same area value, but it's negative. It's below the x-axis. So that's why that area will always be 0. But this one, you said, what about this one? Well, that's not happening here. The area just happened to be what? 0. So that function's not even, it's a neither function. It's neither even nor odd. And you can tell graphically because of the symmetry. Is sine even? Sine is odd. Cosine is what? Even. Symmetric about the y-axis. Anyway, could you guys now do more homework questions, you guys think? All right. We'll see you guys when? Tomorrow. You guys know what's happening. Take care. Stay safe.